This video is an introduction to differential equations. After studying this video, you should be able to understand how to recognize and classify a differential equation in ways relevant to what we'll be doing in this class. You should also be able to understand the nature of a numerical solution to a differential equation and distinguish between an initial value problem and a boundary value problem. So what is a differential equation? A differential equation is a mathematical equation that relates a function and its derivatives. Here's some examples. This first equation describes a spring mass system. This is also called an ordinary differential equation, or ODE, because it deals with only derivatives with respect to one independent variable, that being time. And the solution to this equation would be some function x as a function of time. This next equation is a model for constrained population growth. And here we would have there's some carrying capacity of the population, say due to a limited food supply. And the solution to this would also be a function, some p of t, where p is the total population. And this is again another ordinary differential equation because it only deals with derivative with respect to time. A single independent variable makes it an ordinary differential equation. In contrast to the 2D heat conduction equation, here we're looking at a temperature, the behavior of temperature in time and space. So we have partial derivative with respect to time, partial derivative with respect to x and y, so two spatial dimensions. And so this is a partial differential equation, or a PDE. In Engineering 240, we're going to focus on ordinary differential equations. But the techniques that we use extend to partial differential equations. So how are differential equations used? They are widely used as mathematical models in engineering, physics, biology, chemistry, atmospheric sciences, economics, etc. A very common modeling tool as far as developing a mathematical model if we want to relate rates of change of different parameters, different parts of a system. The natural way to do that is with a differential equation. Often the fundamental mathematics is identical across disparate applications. So here's two example equations. Here's the spring mass equation again, this time with a forcing function added. And this equation on the right is the equation of an RLC circuit. So here we have an equation from mechanics and an equation from circuits. And the mathematics of these two equations is exactly the same. The spring mass equation, the solution is going to be some function x of t, a position as a function of time. The circuits equation, a function is going to be v of t, a voltage as a function of time. And in both cases we have a constant times the second derivative plus a constant times the first derivative plus a constant times the function itself is equal to the forcing function. Same thing for the circuit equation. Constant times the first derivative plus a constant times the second derivative plus a constant times the function itself. And there's a typo there. That should actually be voltage. Numerical differential equation solvers are the basis for most computer simulation software. So any sort of motion simulation, flow simulation, finite element analysis, chemical reactions, all the simulation software such as SolidWorks simulation. If you are in chemical engineering, you might get exposed to Aspen for simulating chemical processes. The guts of this simulation software is all solving differential equations. So let's talk about the solution to a differential equation. The analytical solution to a differential equation is a function. So here's that spring mass oscillator equation again, and under certain values of MC and K, that solution, x of t, would be a function e to the negative alpha t times the quantity a cosine omega t plus b sine omega t. And in this solution, alpha and omega depend on the model parameters m, c, and k, and a and b depend on the initial conditions, and I'll talk more about initial conditions in a minute. Now, when we do a numerical solution to a differential equation, the result is going to be numerical data that represents function evaluations at discrete values of the independent variable. So if we did a numerical simulation to the same differential equation for the spring mass system, we would just get a bunch of numbers, numerical results, but those numbers represent function evaluations. So for example, this first number x, that represents x evaluated at 0, and x evaluated at 0.2 would be 0.8337, and so on. So we are getting discrete numbers, but it represents evaluations of the function, and that's a key concept here. Now, those discrete numbers, it's usually difficult to understand what's happening with the solution, so we'll generally visualize the solution, the numerical solution to a differential equation, with a plot. So here's a plot of the solution to that same differential equation, showing those discrete values. Now the data spacing, or delta t, which would be like 0.2 in this case, that delta t is driven by the accuracy and the computational cost of our numerical solution algorithm. We typically won't reduce delta t farther just to get intermediate values of our solution function. If we want intermediate values of our solution function, for example, if we wanted x at t equals 0.3, in this case, we would do something with that numerical data, and we could use one of the techniques that we've already covered in this class. We could fit a spline to the data to calculate intermediate values. This is a case where we'll generally have what we would consider very accurate data, so interpolation would be appropriate. If we want a functional relationship to do some analysis of our solution, we can do a curve fit to the data to develop some function x equals f of t. Many differential equations have no analytical solution. In fact, probably most differential equations of real practical importance have no analytical solution. They're impossible to solve with analytical techniques. A couple examples here are the van der Pol equation from electric circuits and the Navier-Stokes equations from fluid mechanics. And these Navier-Stokes equations, incidentally, are the basis for everything from weather modeling to flow across an airplane, for modeling lift and drag, to fluid flow in rivers. So wide application of the Navier-Stokes equations. Just to give you a brief overview of these equations, we obviously won't be solving these in this class. This is beyond our scope. But they do contain what should be lots of familiar terms. This is the density rho. U, V, and W are the x, y, and z components of the fluid velocity, respectively. P is the pressure, mu is the viscosity, and g is the acceleration due to gravity. And the reason we have potentially 3 components of g is because our x, y, z coordinate system for applying these equations may or may not line up with the typical z direction going up from the Earth's surface. So if we want to apply a numerical differential equation solver to something like the Navier-Stokes equations, where we have no way of knowing what the analytical solution is, we need to first test that on equations with a known analytical solution. And that's typically what we'll do. So when we develop a new differential equation solver, the first thing to do is apply it to a differential equation where we know the analytical solution. And once we're confident that the solver works well, then we can apply it to a differential equation, probably something that has some similar characteristics but has no known analytical solution. So in order to do that, what we need to be able to do is identify some of the characteristics of a differential equation. So let's talk about classifying differential equations. The first thing that we want to know about a differential equation is whether it's linear or not. A linear differential equation consists of a linear combination of a function and its derivatives. So here's that spring mass oscillator again, and we have a constant m times the second derivative of x plus a constant c times the first derivative of x plus a constant k times x equal to some forcing function, again, f of t. So that would be a linear ordinary differential equation. Again, it's an ordinary differential equation because it only includes derivatives with respect to one independent variable. Here's another one. We have a second derivative of y with respect to x plus 1 over x times the first derivative dy dx is equal to 10. This is still a linear ODE because the 1 over x, that looks like it might be nonlinear, but it's not, because when we're looking for a nonlinear, we're looking for nonlinear terms involving the function itself, y. So we would be looking for something like a y squared, or a 1 over y, or a dy dx squared. Something like that would tell us the equation is nonlinear. So the 1 over x does not make this a nonlinear function. Here's some examples of nonlinear differential equations. That constrained population growth model, we're going to have a p times p, so that p squared is going to make that nonlinear. Here's the van der Pol equation again, and we have two nonlinear terms in the van der Pol equation. When you expand out this middle term, we're going to get a y squared term, which is nonlinear. Also, y squared times dy dt is nonlinear. So recognizing whether an ODE is linear or nonlinear is generally important for determining which numerical algorithm or analytical approach to use. In this class, we'll focus on those numerical algorithms, and most of you will take a differential equations class, Math 261 if it's at a Washington Community College, where you'll focus on analytical approaches for solving differential equations. So let's talk about ODE problem types, since ODE, ordinary differential equations, is our focus in Engineering 240. So we can look first at first order ordinary differential equations, which we'll call initial value problems. And the reason we call them initial value problems is we can write them, any first order differential equation, we can write as dy dt is equal to some mathematical function of f of t and y. And our goal is going to be to determine y of t knowing some initial condition y at t0. So we know the initial state of y at some initial time t, or it might be, the whole thing could be also in space, but it would still be y at x0, some initial position in x, and then we will numerically solve the solution to see how does y evolve in time or space. So this would be a differential equation with one variable and one derivative. We could also have a system of ODEs and have an initial value problem with a system of ODEs, and here we would have some y1 at t0 as an initial condition, y2 at t0 as an initial condition, down to yn at t0 as an initial condition. So systems of ODEs commonly arise in vibration models, also chemical reaction models, and what we will learn later is we can actually write higher order differential equations as systems of first order differential equations. And that will actually be one of the approaches that we use to solve higher order differential equations numerically. So in general, a higher order differential equation, say an nth order defined by its highest derivative, can be written as a function of t and y and all of the lower order derivatives that are involved in the equation. And that nth order differential equation is going to require n conditions in order to have a unique solution. And once we get past the first order, so if we're second order or higher differential equation, you can conceivably have those conditions come in different ways. We can still have initial value problems. So for an initial value problem, we would know y at t0, dy dt at t0, up to the n-1th derivative. So we would know y and all the lower order derivatives, everything known at some initial condition t0. And starting from that initial condition, we would say we would just step the solution forward in time to see how y evolves. We can also have a boundary value problem. A boundary value problem is going to be a little bit different. Boundary value problem, we would know y at different points in time. So we would get our n conditions. We still need n conditions or n constraints, but we get that not by getting a single value, a single initial value of y and its derivatives, but by getting y values at various points in time or space. And these are actually common for problems in space, so some y at x0, y at x1, etc. So we'll look at both of these, whether something is an initial value problem or a boundary value problem, that affects how we solve it, particularly numerically. So the first thing we need to know is it an IVP or is it a BVP? We need to identify that before we can determine what is the appropriate numerical solution. So as we get started in solving differential equations numerically, we are going to start with initial value problems, and then we'll finish with boundary value problems. So we'll do initial value problems first, and then we'll end the quarter with boundary value problems. And that concludes this introduction to differential equations.